Right, I think we're at lecture number 10 for the physics class, guys. This is electrodynamics. So we figured out Newton's laws of motion and then rules of electrostatics, so we can see how there's rules in place that will basically create situations for electrons to start moving and clearing out of orbits. Okay. And then we talked about, electromagnetism, magnetism, and induction, and starting to get the ideas of how you would generate a current with a device like a dynamo or a generator, or now not necessarily a battery, but that's coming up. A battery is just a chemical reaction inside a box. Two different metals, and the electrons jump from one metal to the other metal, and so and then if you connect those posts, the cathode and the anode, with wires, you can get the electrons to run around the wire and back to the other side. Okay, getting into electrodynamics, which is electricity. It's how physicists would say electricity. Is electrodynamics, charges in motion. Okay, so we're going to talk about charges in motion and how Ben Franklin got it wrong. Charge flow, electric current, voltage, current, and resistance. And I do want to spend a little bit of time about how Ben Franklin got it wrong, because so much of the stuff that we learn after this point into the journey of building the X-ray machine, a lot of the stuff relies on use, specifically Fleming's hand rules, which are coming up in the text, relies on the Franklin definition of current, and so we're kind of stuck with it, even though it's exactly backwards. So conduction, conducting materials, resistance, conductors versus insulators, and resistance. Those are all the same idea, the same concept. It's essentially, again, going back to atomic theory, it's different elements, different materials have different levels of resistivity. Things that have very low resistivity, we call those conductors. Things that have high resistivity, we call those insulators. Okay, so it's a sliding scale depending upon what material you're dealing with. In the case of conductors, refined metals like copper, silver, gold, platinum, those type of materials conduct electricity very well. They have low resistance. And then other things that would be probably best described as molecules, rubber, plastic, wood, those type of things have moderate to high resistance, and so we typically call those insulators. And then there's water, and water is tricky depending upon whether it's pure water and if it's in a solid state or not. Water has a variable resistance. If you put a lot of stuff into water, you can enhance its conductivity significantly. Right, and then we'll wrap up the lecture with circuit geometry and sources of the electrons, which are basically the conductors themselves are the sources of the electrons. But we do have to push a little bit of energy into them to get them to free up their valence electrons. Not a whole lot, but a little bit. All right, so we'll talk about current flow. And electrons, basically, they're running downhill, but not downhill in a physical sense. They're running from areas where there's a lot of electrons to areas where electrons are more rare. Okay, and so electron flow is from negative to positive. Okay, and And that's because the convention for charge, Ben Franklin, Mr. Coulomb, several other people working at the time, Ben Franklin is blamed for it. He says that electricity is like a fluid and it flows from abundance to deficit. And he called these positive and negative. And conventional current flow is based on Franklin's definition of current flow, which is from positive, by which he meant abundance of electrical fluid, to negative, which is deficit of electrical fluid. And he was kind of right about abundance deficit, but he got his charge signs wrong because it's actually electrons that are moving around in solid conductors. And so he was exactly backwards. But the whole idea of flowing from abundance to deficit, that's correct. Electrons, though, are flowing from abundance to deficit. So where there's electrons bunched up, they will be self-repulsive and they will seek out areas where there are less electrons around. Okay? Because they'll respond to that repulsive force. So if we give them a pathway to travel to a place where there are less electrons, then they will start wandering in that direction. Okay? And we call that current. Okay? Now, conventional current flow is thought of as the electron holes, that is, the valence vacancies are moving in the opposite direction of electron movement. That's how they try to rationalize Franklin's completely backward idea of positive charges flowing. Okay? Positive charges stand still. We already covered this. The nuclei are massive. It takes much more energy for them to move. But when we get to semiconductors and explaining how semiconductors move charge, this electron hole, that is a vacancy in a valence shell moving in the opposite direction, actually kind of makes sense. All right, so Ben Franklin, when increments became the choice of which type of electricity is called positive and negative, was made around 1750 by Ben Franklin. So everyone calls it the Franklin current when they talk about current. The vector direction for current is the direction of positive charge flow. That's Ben Franklin's fault. Franklin knew of two types of electric charge depending upon the material one rubbed. So he was doing electrostatic experiments and building up electrostatic charges with different types of material like silk and glass, fur, and I think fur and amber, and then wool and rubber. Okay, those were typically the electrostatic parlor tricks of the day. Okay, he thought one kind signified a little excess of electric fluid over the usual amount. He called that positive. Okay, and the other kind was an absence or a deficiency of the electric fluid, and he called that negative. And unfortunately for him, what he termed negative was actually the charged object that had extra electrons on it. A century after that, electrons were discovered, and it was suddenly realized that in metal wires, the electrons were the ones that carried the current. They were the ones actually moving, exactly in the opposite direction of how Franklin's electric fluid was flowing. But unfortunately, that was 100 years later, and we had already developed hundreds of thousands of textbooks on the science of electricity based on Franklin's work, and everyone building off of Franklin's work. And so Michael Faraday had already done his thing, and we had already developed electricity and understood the difference between DC and AC. and all this stuff. We had the science for electricity down. We had Maxwell's equations. We had everything. Everything made sense. It all worked. And then J.J. Thomson said, actually, it's electrons that are flowing. The negative is flowing, not the positive. So, yeah. They actually convened a conference of physicists, and I've lost the citation, but it's on the internet somewhere. They convened a conference right around the time of Rankin's discovery. I think it was shortly after 1896. It might have been 1897. They convened a conference of electrical engineers and physicists and voted whether or not to change the definition of current. And they voted to keep it because, yes, college professors are lazy too. They didn't want to rewrite all their textbooks. All right. So the caption, we'll start with the caption at the bottom before we go into the dialogue. We were going to use the time machine to prevent the robot apocalypse, but the guy who built it was an electrical engineer. And so now we can have the humorous conversation. This is a electrical engineer jumping out of a rift in space-time. Ben Franklin, yes, I bring a message from the future. I don't have much time. Which is not true. If you got a time machine, you have all the Marty McFly, you have all the time that you ever need if you have a time machine. The convention you're setting for electric charge is backwards. The one on the left on glass by silk should be the negative charge. This is how much it bugs people. And please ask Mr. Shepard about current and electron flow. And yeah, watch his face get red. He'll get very frustrated very quickly. I, however, think that this is amazing because it is science in a nutshell. We think we have everything figured out, and then we run another experiment, and it proves us wrong, and then we have to rewrite all the definitions and rework all of our theories because some guy dreamed up some new experiment and proved us wrong. And that's the story of science. So the story of electric current being backwards is a microcosm of the story of all of science. And so I think it's funny. I think it's awful confusing for students, and that's unfortunate. But it's funny. It's irony. It's great. You know, we revere Ben Franklin he was a pretty bright guy, enterprising, had, invented the post office, invented the lightning rod, mail delivery service, wrote an almanac, was a businessman, was an ambassador to France, was key in getting France to join the Revolutionary War. Just a really remarkable man. But yeah, this one thing in the physics universe, everyone kind of shakes their head when they think of Ben Franklin. So, I actually went to Philadelphia in, I think it was, April of 2024. Took a little trip to Philadelphia with my son, and they have a museum of Philadelphia history. Well, they have a science museum. They have a museum of Philadelphia history. And at the science museum, these are actually Ben Franklin's electrical experimental tools. Okay. So here on the left, his lightning rod was actually connected to a bell. He had a suspended metal armature on a pivot, and then he had two brass domes. And then there was a connecting rod going up to his roof to the lightning rod. And then the brass dome on the far left ran into his basement and into the ground. And so what would happen is lightning would strike the lightning rod, and it would charge the brass bell on the right, and that would create electrostatic attraction, and it would cause that armature to oscillate back and forth between the two bells until it discharged all of the excess charge on the bell on the right to the ground. And so it was a cool apparatus, such that in Ben Franklin's house, when lightning struck his lightning rods, it would ring these bells and he could tell that it was working. It's pretty neat. Okay. I was surprised to find top right, he had a vacuum evacuated cathode ray tube. Essentially, I'm not sure what model this was, but it looks very similar to like an elongated Crookes tube or a Geissler tube. And so he was doing cathode ray experiments. He was charging one side and charging the other side with the opposite charge. And apparently he was probably making this tube glow because electrons were whizzing back and forth between the two, the cathode and the anode. So, all of these tubes are precursor to the X-ray tube. So I thought that was fascinating that even Ben Franklin was messing around with and could have accidentally discovered X-rays. And then this down here, these are called Leyden jars, and they are precursors to batteries. And he has them wired up in series, it looks like. So early Leyden jars were early editions of chemical batteries, and they would just put in, I think they had a collar, or the outside of the jar was coated with one side of the metal, and then there was a rubber gasket, and then you dropped in the lid was fashioned with a metal rod inside, and then you filled the thing with acid, and the two types of metal were different, and you would conduct electricity between the outside of the jar and the inside of the jar. And so it's a crude battery. It's called a Leyden jar if you want to look that up on the internet. Okay, so the quantity of electrons flowing, or the rate of charge flow, is called current. And it literally is the unit of measure for charge. You remember from the Coulomb force, the product of the charges over the distance is the force. Well, current is charges flowing, that is, again, Q, the quantity Q, over seconds, time, okay? So you basically take a point in the electric circuit and you measure how many electrons are whizzing past per second, okay? And it's literally coulombs per second. Now the other quantity of electricity is the force applied to the electrons that's making them flow, okay? So you can kind of think of current like velocity, and then voltage is the force, okay? Voltage is always talked about as a potential energy or a form of potential energy, but it really is a force. It's the sum of all forces pushing and pulling on the electrons, okay? And so I've already given away the answer to this question for current, but if voltage is electromotive force, which it totally is that a vector or a scalar? And you should know the answer if it's a force. Yeah, it's a push or pull, so that doesn't really make sense without a direction. And so both of these are vector quantities. And that's going to be important to us as we proceed further in our study of electricity, to remember that both current and voltage are vector quantities, and they also have a cause and effect relationship, just like force has a cause and effect relationship with acceleration. Voltage is the cause, current is the effect. Okay, and then we got to talk about opposition to current flow. Now they call it impedance or resistance, and depending upon whether you're working with alternating current or direct current, they have two different names for it. I just call it resistance. Okay. I've heard that they were synonyms, but then this textbook makes it a point to say, well, it's kind of different in alternating current versus direct current. Resistance is a scalar quantity, and it really is it is a chemical property of the material, so it's tied to the identity of the material that you're traveling through. Okay, and so we will see resistance or resistivity is variable depending upon, are you dealing with copper or glass, because you can push electrons through one, but you can't push electrons through the other. Okay? And so yes, there is a voltage, but you can't just apply a voltage to anything and expect electricity to flow. You have to have a low resistance material. Okay? In fact, in most electric circuits, we add resistance so that we don't get runaway currents, because copper is just all too welcoming and letting electrons go through it, to the point that copper will melt before it stops the electrons going through it. Okay? So we have to add more resistive materials to our circuits so they don't burn up the copper wires. Okay? Now, the direction of travel, alternating current versus direct current, I believe I talk about that further in upcoming slides. So, but there is two different ways that current flows, primarily alternating current and direct current. Okay, so yeah, here we go. This is direct current. Direct current means the flow of charge is always in one direction. Okay, both the Franklin definition of current and also electron flow. They're in opposite directions. Okay, Franklin current is positive charges. So if you have a wire and the Franklin current is pointing to the right, then the electron flow is actually to the left. Okay. Voltage can be supplied by a battery or a DC generator. Right. We will briefly talk about generators, but that's the electric power company. We just assume that when we connect the X-ray tube or the X-ray machine to the hospital wiring, that electricity is being supplied. Okay. Advantages to a direct current are, if you're utilizing a machine or an electric circuit that is relying on direct current, portability. If you can make the battery small enough, like inside your cell phone, you can actually walk around with an electric circuit in your pocket, or several electric circuits in your pocket. Energy storage. Batteries are the storage place, capacitors too, but batteries are storehouses of voltage. So the force is stored as a potential energy. It's really stored as a chemical energy. Stability. DC power supplies are very reliable until they're not, until the battery dies. Incorporate renewable sources like solar power. So solar technology is primarily a DC type technology. It supplies direct current type electricity. Some devices require DC to operate. Most of our computers, cell phones, and most circuit boards run on DC electricity. And you can get a more consistent voltage out of DC, necessarily. It's a more constant voltage, most times. Okay. Alternating current. And these graphs, pay attention to those. Those are voltage versus time. So as time goes, in DC, on the previous slide, voltage is constant, regardless of what time you measure it on that circuit. If it's a DC circuit, the voltage is always, the force being applied is always in the same direction and the same magnitude. In an alternating current, we cycle the voltage back and forth, so it changes direction. And remember when we said deceleration, we represent that by a negative value for the magnitude. Well, a negative value for voltage means that we reverse the vector direction for the voltage. So every time you see a crest in one of these waves, the voltage is flowing, let's say, to the right. That means that since we defined the crest voltage pushing to the right, when we encounter a trough, the voltage pushes to the left. And so what ends up happening is the electrons, instead of moving down the wire and all the way through the loop, they move down the wire one way, and then they come to a stop, and then they move back in the direction they came. So they kind of wave back and forth, or oscillate, so to speak. Okay? But we can still get work out of them. We can still create a changing magnetic field. We can still create electricity in this way. It just is a different form of electricity. Now, to create electricity, recording in the winter when your nose is congested from the artificial heat in the rooms and all the cold, the changing from hot environments, cold environments back. It's just miserable. Okay. So voltage created for AC, or the generator for it's got to be an AC generator. It's got to be a dynamo, basically, which Mr. Faraday invented. There is no battery type device that can create alternating current. The advantages to AC power generation is it's simpler and cheaper as far as infrastructure goes. You can send AC for a longer distance. Think about like the electric grid and the power lines running from the power plant. AC is supremely superior at pushing electricity over miles and miles. As we'll see in the movie, that was the distinct advantage of Westinghouse over Edison and trying to build an electric grid across the country and supply electricity to entire towns or entire counties. Voltage and current can also be transformed by transformers, and so you can modify the voltage and current much more simply and easily. Transformers also invented by Michael Faraday. Okay. Some devices require AC to operate, specifically motors. In fact, your alternator in your car, it's part of your car that recharges your battery, is an alternating current device. It is an AC generator. But other motors, like I think an electric bicycle runs off an AC generator. Home appliances, your vacuum cleaner runs off an AC generator, or an AC motor rather. Any electric fans that you own, those are AC motors. Several, I think your microwave oven has to be an AC device too. So your hair dryer, your curling iron, your toaster, all those are AC devices. Okay. So getting back to current as a measurement, it's the quantity of electrons flowing. Okay, and it is, so we figured out the SI term here for measuring quantities of charges. That's in units called coulombs, capital C. 1 coulomb is 6.2 times 10 to the 18th charges. Okay. If we have that many electrons flowing past us in 1 second, then we have an ampere, or amps. Okay? And so you should recognize ampere, or at least a fraction of an ampere, a milliamp, from X-ray machine technique, yes. And so when you set mass, you're setting milliamps and seconds. So you're really setting coulombs or millicoulombs. Okay? And so if you remember that, then you will have no trouble remembering that the number of electrons flying across the X-ray tube is the mass. Because if you solve ma times time, and you substitute in coulombs per second times seconds, well, you're dividing and multiplying by seconds, so they cancel out, and so you're left with coulombs. And so mass literally is the quantity of charge. All right, potential difference, electromotive force, voltage, all of those are synonyms. Okay. So when we're thinking about a battery, we like to call it potential difference because it's a potential energy possessed by the battery. It's a potential to push on electrons. Okay. It is a force because when you're talking about the forces, summing all the force vectors that the electron is experiencing while it's in the electric circuit, that is the voltage. Okay, so take all the force vectors, both repulsive and attractive, and that's the voltage. Okay. Voltage is joules per coulomb, and so it's how much energy is imparted to each charge, but it does have a vector to it. Okay. Yes, both joules and coulombs are scalars. So, yeah, kind of doesn't make sense, but also makes sense. Areas of higher and lower concentrations of electrons, an ordered system. What happens over time? Oh, law of thermodynamics, entropy. We have a sorted system. So if we create in our electric circuit bunching up of electrons in one place and an absence of electrons in another place, well then, as time progresses and the electrons have a pathway between those 2 points, they're going to tend toward disorder. That is, they're going to try to get themselves unsorted from high concentration to low concentration. So it's like there's a potential energy that turns into a kinetic energy. Yeah. Aren't you guys glad I taught you mechanics and thermodynamics and energy, so you can understand, you can get, there's that beauty that flows out of it. Oh, the electrons don't like being bunched up, and so they're in a higher energy state because they're bunched up. Yes, they are. Okay. And matter likes to return to a ground state. It doesn't like for electrons to be bunched up, and so the electrons will try to run away from each other. Now, resistance. Remember that the copper wire is made out of atoms. Okay. And so, yes, it loses its valence electrons, but it's got another shell of electrons. And so we're talking about the electrons in the material of the conductor that are not flowing. Those are going to offer repulsive forces to the electrons that are flowing. Okay. And they're also going to steal some of the energy from those flowing electrons and slow them down. And so resistance is thought of as a property of the material. It's an opposition to the current, but it doesn't have a vector. It doesn't have a direction. It's a scalar quantity. And it's dependent upon four things. Now, if you're going to be an electrical engineer, you have to remember these to pass your electrical engineer certification exam. The overall conductivity or resistivity, the length of the wire, the diameter of the wire, and the temperature of the wire. Okay, all those things make the affect the resistance. Okay, so if the temperature gets hotter, the resistance increases. If the length of the wire gets longer, the resistance increases. If the diameter of the wire increases, the resistance decreases. And then as the material becomes more conductive, it is less resistance, so the resistance decreases with increased conductivity. Now, yeah, there are two different names, but I'm not going to quiz you on that. You're not going to find that in the registry, in the credentialing exam. I passed my registry without knowing this. I only learned this when I read this book. Okay? So in DC, it's called conductance, and in AC, it's called admittance. Yeah, okay. We'll just call it resistance. Okay? All right, so the material's conductivity, it's largely dependent upon the valence band. Does it have loosely bound, just a few loosely bound electrons, like copper? That's great. That's perfect, in fact. Okay. Is the conduction threshold, that is, the ability of the electron to just wander free, does that take a great amount of energy to get it out of the valence? So the difference between the energy, the binding energy in the valence band, and the energy threshold for the electron to wander free. Is that a huge difference of energy or a very small difference of energy? And for copper, it's actually a negative difference. That's right, copper's valence shell binding energy is so low that its conduction threshold is below the valence shell. It really doesn't hold on to its valence. Yes, we put, for a Bohr model, we're going to put the electrons there, but in reality, they really don't stay there. They wander around. They just hop from copper atom to copper atom, unless a voltage is applied, and then they start wandering in one direction. So conductors have valence band and conduction band overlap, like copper. Semiconductors, the energy gap is really, really close. It's really, really small. And then insulators, the band is extremely far apart, and it takes a ridiculous amount of energy. Combustion happens before electricity happens for insulators. So wood, you can hook a 2x4 up to a battery. You can drive a nail into one end and drive a nail into another end and push voltage through 2x4, and the 2x4 will catch fire before you can measure any current. So yeah, insulators, yeah, you're just not conducting electricity through wood. You'll set fire to the wood, but it won't push current because the resistance is so high. So I totally stole this from the internet. You will not find this. It belongs in the X-ray science textbook, but you won't find it. So resistivity as a property of the material you're dealing with. And you can see metals and alloys are good conductors. Composites, those would be like ceramics. Porous ceramics, there you go. Composites, those would be other types of materials. Now, what fits into composites? I would say acids and bases fit in there, because acids and bases are fairly good conductors. You know, like battery acid. Why do we fill the battery bucket with acid? Well, that's because it allows charges to flow through. Just don't ask Mr. Shepard what type of charges are flowing through the battery acid. He might get frustrated again. Wood and wood products, poor conductors. but not necessarily good insulators either, and that's because they catch fire. But also, I would say your polymer plastic is going to catch fire too eventually. So, but yet we shroud all of our wires with polymer plastic typically. They used to use paper, I think, back when Faraday, and he had to hand wind his insulation. And paper was just a commodity that was available and cheap, so they just wrapped the wires in paper. Yeah, paper is highly combustible, so that didn't turn out good. Yeah. And then glass. Ceramics are very variable, and I don't know why they don't put ceramics with composites. I don't know. See, that's the problem with stealing this off the internet. I would make ceramics into composite materials, but maybe they're thinking earth as a composite material. I'm not sure what they're thinking of there, why they separated ceramics. But some ceramics can be made into reasonable, it's not like copper wire, but reasonable conductors. So, all right, and so this is the book's version of that chart and showing you the electron shells. And so you got to think of this as, remember I said the Bohr model wasn't a physical model, it was showing you the energy states of the electrons. Well, if you give the electrons enough energy, they'll leave. And that's what we mean by conduction. So conduction is the electrons leaving the individual atom, but it's still in the material, and it's basically responding to the voltage, which is the energy you're giving to the material. And so some materials genuinely conduct, some materials conduct in certain circumstances. That's our semiconductor materials. And then some materials just do not conduct. The gap between the valence band and the conduction threshold is too great, and you end up getting, you push energy into those insulator materials, and you get combustion combustion shows up before conduction shows up. So, all right. And again, length with conductivity, resistivity. Yeah, we say copper is a good conductor, but there is an upper. You can connect a battery to copper wire, and as long as you're under like 20 feet with 12 volts, yeah, you'll probably get electricity out the other end of the 20 feet of copper wire. But if you go 3 miles or 6 miles or 100 miles, yeah, the resistance is going to build up, and you're not going to get electricity out the other end. So, not with the DC. So electricians, when they wire buildings, they keep this in mind, because they know that the resistance is going to build as they run more and more wire conduit through the building. So, the diameter of the wire, thicker wire, so when we are transporting electricity on the power lines, we're using thicker wire because we want lower resistance. And so again, if you're an electrical engineer, you would have to know the different gauges of wire, and you know that you could push with larger diameter wire, you can push more current with less resistance. Okay. You will not have to know that for my quiz. Oh God, it's the red ring of death. Okay, so sorry, I burned up 2 Xbox 360s from the red ring of death, and so they will forever be memorialized in my electrodynamics lecture. So temperature affects resistance, and so if you have a circuit board in a video game system, but you have it engineered it such that it can bleed off the heat, looking at you, Microsoft, you could save a couple bucks by not fitting your circuit board with a heat sink, which is the left-hand picture. But you're going to upset your customers because your crappy video game system is literally going to fry from heat. So, and then they get the red ring of death. Okay, and so when we build circuit boards, like in the X-ray machine or any computer, you have to allow for heat dissipation because circuits will get hot. They just will. And if you don't allow a escape route for that heat, then you're going to end up getting a circuit board that traps heat. And if dust comes along, dust is an insulator, and it will insulate your circuit board so it will necessarily hold on to the heat even more efficiently, and then it will just burn up the circuit board and the circuit components. So, and then you get the red ring of death, and then you have to go and either get your Xbox rebuilt or just buy a new one, which I think back when that was happening, it was basically the same price, and so it wasn't worth it. Notice they didn't issue a recall. Yeah, because they didn't want to lose their shirt. It was 100%. It wasn't a question of if your Xbox 360 was going to burn up its motherboard. It was a question of when. So, yeah. I am glad to see that the Xbox 360 has been replaced. But the PlayStation is superior. Just saying. All right, moving on. Ohm's law, and so now there should be a vertical line between the I and the R, right? And so V equals IR, and again, if you're learning electrical engineering, you use I for current, all right? But we're in X-ray school, and we use technique, which is kVp and mass, and so we're used to the A, and so I've written Ohm's law for the X-ray curriculum as V equals A times omega. And so that's how you'll see it on my quizzes, because I want you to think of kVp and mass when you see this formula. Okay. And then triangle notation, so you can cover up any of the unknown variable with your finger, and then you get the equation for how to solve that. So V divided by R gives you current. V divided by current gives you resistance, and then resistance times current gives you voltage. Okay, so this is a math equation, so let's do some math. A simple circuit is constructed between a light bulb and a power supply. If the resistance is 3 ohms, and the battery produces a potential difference voltage of 1.5 volts, what is the current in amperes? Okay, so for V, you would substitute in 1.5. For omega, or ohms, you would substitute in 3, so you get 3 times A equals 1.5. All right, divide both sides by 3, and you end up with 1/2, or 0.5. So that amps is 0.5 amps for that first one. Another circuit has a voltage of 12 volts. Okay, so we're dealing with an automobile battery, but only produces a current of 2 amps. What is the resistance in the new circuit? Okay, so again, substituting in, we have 12 equals 2 times omega. Okay, divide both sides by 2, and you get 6. So the resistance of this second circuit is 6 ohms. Hopefully that was pretty straightforward for most of you. It's just a multiplication or division problem. Power, more obligatory. Okay, so power will come up They mention it in the X-ray text, but they really in this text by Carl, but they really don't say where it applies to. Power is going to show up in the heat units formula, and it's also going to show up in the transformer, okay, and our understanding of the transformation that's happening in the transformer, which will be, I believe it's one of the upcoming, let's see there, I think it's 2 lectures more to go and then we get to the transformer. So power in the book is IV. Again, they're using I like we're electrical engineers, but we recognize it as A, amperes. Okay, so I've just converted it to V times A, volts times amps, equals power in watts. Okay, and now you're thinking of your electric bill. And yeah, it really is I believe it's a rate of energy consumption, but don't take my word for it. Voltage, remember I said, was joules, energy per coulomb, and then amps was coulombs per second. And so if you multiply those two together, lo and behold, coulombs cancels out and you get joules, energy, per second. So watts is literally a rate of energy consumption. And that's what power is. It's the rate of consumption of energy by the circuit. All right, and then finally, getting down to the end of the lecture here, circuit geometries. And so electricity behaves differently, the voltage and the amperage behave differently if we have one pathway or multiple pathways. Okay, so the series circuit is typically single pathway. From the power supply, we have a battery over there, and then 3 resistors. Okay, so the electrons flowing out of the cathode of the battery have to go through all 3 resistors to get back to the anode of the battery. And that creates a unique set of circumstances or a unique set of rules versus in the parallel circuit, the electrons can choose to go through resistor number 1 or resistor number 2 or resistor number 3 to get back to the battery. And so intuitively you might think that the current partitions in the parallel circuit, and you would be right. But the current doesn't partition in the series circuit. You would also be right. And that sets up the rules that we have to learn about parallel and series circuits. So for series circuits, the total resistance is equal to the sum of the individual resistances. That makes sense. The electrons have to go through all 3 resistors. So it's like they're going through one big resistor, the magnitude of which is all 3 of those resistors. Okay. The current through each circuit element is the same and is equal to the total current. In other words, current is constant in series. The sum of the voltages across each circuit element, so the voltage across resistor 1 plus the voltage across resistor 2 plus the voltage across resistor 3 is the total voltage supplied by the battery or the generator. Okay? And so do you have to remember all of these? No, I want you to remember what's constant, because that's what applies to learning the X-ray circuit. So if we had a meter, let's say an ammeter, that measures current, how do we want to wire that in relative to the X-ray tube? I'll let you think about that. It'll take a couple lectures before I give you the answer. But think about what we talked about here, and how do you want to measure current if you're trying to estimate current because we can't put an ammeter inside the X-ray tube. So how would we accurately measure tube current from outside the X-ray tube in another place in the circuit? Rules for the parallel circuit. The sum of the currents through each of the resistors is equal to the total current. So that is the current partitions, because the electrons have a choice. They can go through resistor 1, resistor 2, or resistor 3. Voltage, the force acting on the electrons, is the same no matter which path they choose. The total resistance is the sum of the reciprocals. So the reciprocal of the total resistance is the sum of the reciprocals of each of the individual resistances. Wow, that is complex. Which one do you have to remember? Which one is practical for X-ray science and learning the X-ray circuit? Voltage is constant in parallel. So again, if we wanted to measure the voltage across the X-ray tube, but we can't put a voltmeter inside the X-ray tube, how would we wire it into the circuit so that we could get an accurate estimate of the voltage in the X-ray tube? That's why you have to know these two rules. All right, we have discussed electricity and all of the parameters of electricity that we understand or we need to understand for understanding the X-ray circuit. Voltage, current, resistance. That's all. Oh look, just under an hour total. That's fantastic. Time for me to go, gang. I'll see you next time.